Welcome to this explainer. Today, we're doing something really exciting. We are completely unboxing artificial intelligence. We hear about AI literally every single day, right? But so often, it's just treated like this impenetrable magic trick. Well, today, we're stripping away all that mystery. We're going to lift the hood, look at the actual nuts and bolts of machine learning, and see exactly how it maps onto our everyday analog world. No sci-fi, just the real mechanics. Here's our roadmap for today. We're covering 5 key areas. First, AI fundamentals and mechanisms. Then, the evolution of AI. After that, we'll hit structuring knowledge and data, followed by AI implementation in society, and finally, data protection and privacy. Let's get right into it. Section 1. AI fundamentals and mechanisms. To truly understand AI, we first have to look at the engine that drives the whole thing. So, what is a neural network? Fundamentally, it's actually an imitation of our own brain's biology. It's designed to process complex information systematically. Think about how human nerve cells pass signals to one another. Well, a neural network does the exact same thing, just with data. It takes raw information, analyzes it through a web of interconnected nodes, and pushes out a calculated result. But how does that data actually travel through the system? It basically builds in a 3-step journey. First, data enters the input layer. You can think of this as the system's eyes and ears. Then it moves into the intermediate or hidden layer. This is where the real heavy lifting happens, where the system teases out features and recognizes patterns, curves, or specific data points. And finally, the output layer delivers the final prediction or result. But for the AI to actually give us an accurate result, it has to fine-tune its internal dials. And this brings us to a really fascinating balancing act: weights and biases. Weights essentially decide how important a specific clue is, while bias gives the system the flexibility it needs to find the right answer. Imagine the AI is trying to predict the weather. The weight tells the system, hey, dark clouds are a massively important factor for rain. But bias acts as an intentional shift. It lets the model adjust its baseline so it doesn't just rigidly scream rain every single time it sees a slightly gray sky. Together, these two factors dictate the true intelligence of the model. Moving on to Section 2, the evolution of AI. Now that we know the mechanics, let's look at the historical blueprints of how we actually arrived at this point. AI absolutely did not just appear overnight. It was built in distinct generations. In Generation 1, we had the simple perceptron, which could really only handle basic straight-line classifications. Then, Generation 2 brought the multi-layer perceptron, adding those hidden layers we just talked about, which allowed for complex, nonlinear patterns. Generation 3 introduced expert systems. These were rule-based and great at things like specific medical diagnoses, but they completely crashed into what we call the wall of common sense. They just totally lacked human intuition. Which brings us to Generation 4, modern deep learning. This is what powers systems like AlphaGo, using massive simulations to make intuitive leaps. What's really wild is that long before AI was actually smart, it was already tricking us. Have you ever heard of the ELIZA effect? It's this psychological phenomenon where humans feel a sense of human likeness from a mechanically responding program. Basically, artificial incompetence. ELIZA was an early program that did nothing but reflect user statements back as questions. Zero actual understanding. Yet people literally poured their hearts out to it like it was a trained therapist. It's a great reminder that we are psychologically hardwired to find meaning, so we always have to separate our emotional response from the machine's actual capabilities. All right, Section 3, structuring knowledge and data. Because raw data isn't enough. AI needs structured knowledge to truly understand our world. Think about it. Dumping a dictionary into a computer doesn't teach it how to read. We have to organize concepts into an ontology, or a semantic network, giving the computer a map of logical relationships. For example, the AI needs to know the is-a relationship, like a light car is a car, so it inherits its traits. It needs to know the part-of relationship. A tire is part of a car. And ownership, like a car has tires. It's building a web of meaning. Without these strict definitions, the system's logic completely falls apart when it tries to combine different concepts. And this is incredibly difficult to get right. Take the Torobokun project in Japan. The goal was for an AI to pass the rigorous Tokyo University entrance exams. It actually achieved a deviation score of 57, which is above average. But it highlighted a critical limit. It failed to get in because passing is incredibly difficult with knowledge alone. It completely lacked true reading comprehension. It proved that just linking facts together is absolutely not the same thing as genuine human understanding. Section 4, AI Implementation in Society. Now that we've seen the engine and the blueprints, let's watch the car actually drive on the road. Level 3. This single number represents a massive societal shift. Following a 2021 law change, Level 3 autonomous driving allows the system to take full control under specific conditions. At Level 3, the car is driving itself, and a human only steps in if the system requests it. The legal update in Japan even allowed drivers to use their smartphones while in this mode. This is AI moving from theoretical data to reshaping our physical highways and actual laws. It's a real game changer. But bringing this kind of tech to the market, it's not magic, and it's definitely not easy. It requires a highly structured standard, like the CRISP-DM framework. You can't just build a model because it looks cool. You have to start with business understanding. What problem are we actually solving? Then you move through data understanding, data preparation, modeling, evaluation, and finally deployment. And the key here? It is a continuous loop. AI projects are never truly finished. They require constant iteration to maintain their value. And when it comes to deployment, teams have a big choice to make: agile or waterfall. If you're building a service that needs highly flexible, constant improvements, like a recommendation algorithm, you're going to go with agile short cycles. But if you're deploying AI into a regulated hardware system where a mistake could be catastrophic, you'd likely choose waterfall's sequential, strictly managed progression. The deployment strategy totally dictates how the AI lives and breathes in the real world. Section 5, Data Protection and Privacy. As AI devours data from our everyday lives, we desperately need to talk about safety features. Let's look at 3 major privacy safeguards, starting with differential privacy. This is a highly advanced technique that cleverly mixes random mathematical noise into data. Imagine a database showing the average age of a group. The overall average remains highly accurate so the AI can learn, but if a hacker tries to reverse engineer it to find your specific age, that added noise makes it exceedingly difficult. You are literally protected by mathematical static. Next up, we have federated learning. This is brilliant because the AI model learns locally, right on your individual device. So instead of sending all your private text messages up to a vulnerable central cloud to improve predictive text, the AI comes down to your phone. It learns from your typing locally and then only sends the learned improvements back to the main server. No raw data leaves your hands. It is a massive win for reducing leak risks. And our final safeguard is TAE anonymity. This is a processing technique that balances statistical value with anonymity through data generalization. It basically ensures that at least K number of records share the exact same attributes. So if K is 5, the system alters the data, say changing an exact age of 32 to a generalized range of 30 to 35. That way, your record looks identical to at least 4 other people in the database. You're always hidden inside a crowd. As we wrap up this explainer, I want to leave you with a critical question. As AI systematically maps our analog world into digital data, how will we balance the drive for ultimate business efficiency with the absolute necessity of our personal privacy? We've seen the microscopic mechanics, the evolution, and the frameworks. The potential for innovation is absolutely boundless. But this tension between progress and privacy, that is going to be the defining challenge of our era. Thanks so much for joining me on this deep dive. Keep questioning, keep learning, and I'll catch you in the next explainer.